In the story of science, there are some photos that capture more than just a time and a place.
Iconic images not only help us define history, they also have the power to change how we see the world around us. I'm reminded of that classic picture of the Earth taken from the moon. We'd long known that the Earth was a planet floating in space, but to actually see that first picture of the Earth surrounded by the blackness of space really cemented it in our understanding.
Right now, scientists around the world are getting together to take a new iconic image. It's of something you can't even see. It's a place in the universe where the laws of physics break down. It's a black hole.
We're going to catch a glimpse of this guy, and I'm pretty excited.
It's a journey that's taken close to 100 years, from humble beginnings in the outback.
This is the photographic print.
No way.
Taken at Yelda and developed here in Broome.
That is so cool.
To our new generation of black hole hunters,
Come on, that's a beauty.
stalking them down in the night.
Gotcha, it was nearly impossible, but here you are.
The first one?
I'll be following these world-leading cosmologists as they close in on their prey.
Out there is an orchestra of black holes, each with their own special sound.
It's all part of building a bigger picture of what black holes are and taking us close to the very edge of a black hole for the first time.
Right now, we are on the cusp of a very ambitious project whose goal is to achieve what may prove to be one of the most iconic images in human history.
What we find there could reveal how extreme they really are.
We're just about to open up a new field of science.
It could even overturn the laws of physics.
It's always more exciting to show the theory is wrong.
This is the story of the black hole hunters. How do you draw something that no one's ever seen?
Could I draw a black hole for you?
Do this on camera.
It's not easy.
No.
It really isn't.
I'm a terrible artist.
I kind of envision a silhouette.
I've got this shrinking space.
Few objects in our universe inspire as much intrigue and wonder as black holes.
See some gas, it's flowing in.
Let's show a black hole. That's not satisfying.
Nothing can escape.
They're the ultimate testing ground for the physics that governs our world.
I spent a lot of my life looking at this fuzzy blob.
Our current understanding of them is a mix of hard-earned science
I believe that the black hole in the center is spinning.
with a pinch of imagination.
This is the place you don't want to fall into.
But now we're getting close to knowing what a black hole really is.
And the vision is to get this perfect ring.
Finally, you come to this place where time stops.
I'm Professor Tamara Davis. I'm a cosmologist and I also study black holes.
So what is a black hole? Don't be fooled by the name. It is not empty space. It's a really extreme environment, and the key to understanding it is gravity. We're all familiar with gravity here on Earth. You know, if I jump up in the air, it pulls me back down. But if I really wanted to escape Earth's gravity, I could jump in a rocket, shoot off into space, and never come back. A black hole is different. A black hole is a place where the gravity is so extreme that nothing can escape, not even light. How could a black hole possibly form? In every star, a battle is raging between the nuclear furnace in the center pushing outwards and gravity pulling inwards. Now that battle can rage for millions or billions of years, but eventually the fuel runs out and gravity wins. The whole star collapses in on itself, and in the resulting explosion, if the star is big enough, nothing can prevent the core from collapsing completely, and we're left with something extremely small and extremely dense. Imagine a place where gravity was billions of times stronger than on Earth. So forceful that it would take the entire Earth and everything on it and compress it into something the size of a marble. That's a black hole.
The story of their discovery begins 100 years ago. At first, they were just something that came out of mathematical theory. No one had ever seen them. And one of the earliest hints that they might really exist, strangely enough, happened right here in Australia. I've come to one of the more remote parts of Western Australia, to this Broome bowling club, a place I wouldn't necessarily expect to be linked with the hunt for black holes.
How's
How
it
are
going?
you? Yeah, good.
You must be
I'm
Robin?
meeting up with local historian Robin Wells.
On a stinking hot day.
It is.
She's interrupting a game of lawn bowls to show me the spot where nearly 100 years ago, one of the most important images in science was processed.
So we're standing right here now,
Yeah.
looking at these two buildings. That's the building where the plate with the star images was
Yep.
developed. So right here in
That's
that building.
so exciting.
In 1922, the remote outback station of Wallal, some 300 kilometres south of Broome, became the centre of the scientific world. Famous astronomers from as far away as California in the UK made the difficult journey there by rail, sea and even donkey to this little part of Australia, the perfect spot to catch the next total solar eclipse. An event that was to prove a turning point in the story of black holes. Their aim was to test Albert Einstein's theory of relativity, which suggested that very large objects in space could bend the path of light. What's that got to do with black holes? Well, if his theory turned out to be correct, it meant that black holes could exist.
There's 30 tonnes of equipment. So there was a 40-foot telescope that they brought with them. There was 5 cameras. They had to be meticulous. There was really, really high expectations. The eyes of the world were on them. The eyes of Australia were on them, and people wanted results. When you read their reports, they're just like, fumbling, practicing. They just practice for hours every day, like going, yep, right, 1, 2, put the plate in, take it out.
But it's not digital camera era, we're talking like glass plates with photographic emulsions on them.
After weeks of practice, the scientists only had a few minutes to capture the image.
The shadow of that eclipse came directly over Wallal, and as I say, perfect conditions. They had their 5 minutes where they were able to take all the photographs they needed.
The photographic plates were taken back to the darkroom, which is now this trophy room in the Broome Bowling Club.
This is the building where the photographs were developed and the star images were measured. So it's extraordinary, right here.
This is where it all happened.
Yep.
The stakes were high. They had just one chance to develop the image that might confirm Einstein's theory.
That pressure beforehand and the stress they must have been feeling, did it work? And they're developing the plates and pulling it out and that,
Yes, we've got it.
yes,
We've got it.
that's amazing.
It's now 100 years old, But that photo was an important glimpse into how the universe works.
So, Tamara, I've got something to show you.
Oh, really?
This is the photograph that was developed,
Really?
taken on a glass plate in 1922 at Wallal. This is the photographic print
No way.
taken at Wallal and developed here in Broome and measured here in Broome.
That is so cool. I mean, check out the eclipse. The eclipse is beautiful anyway. You can see this beautiful black disc and the corona coming out from the outside, so you can see like the edge of the sun. But it's really impressive that you can see these. You can see all of the little stars.
When I saw this, I was just bewildered. I thought someone had taken a texture or something and put white circles. It's actually the light of the stars.
They're doing this to measure the positions more precisely, I bet. But they didn't have the stars just as dots. They made them rings so you can measure the positions. You can do that with different focusing of the telescope and stuff. That's crazy. I honestly hadn't even thought about how they did that in practice. That's really cool. That's very clever, actually.
It's a really, really beautiful, beautiful photograph.
Feels very sort of heartwarming to hear the story of my intellectual ancestors converging on this spot to try and confirm that relativity really is the correct theory of gravity.
Yeah,
So,
it happened.
Yeah.
Yeah.
The photographic evidence was irrefutable. When the position of stars around the eclipse were compared to photographs taken beforehand, the stars appeared to have moved. But why?
when we're on Earth, looking at distant stars, we see them where they actually are because the light has travelled a straight line to reach us. But when the sun passes between the Earth and the distant stars, its gravity bends the light. So it looks like, if you trace back, the stars are out here. So it's measuring the difference between where the stars actually are and where they appear during an eclipse that confirmed Einstein's theory of relativity.
So if light can be bent by the gravitational pull of a big object like the sun, then something even more massive could swallow it entirely. And that would leave a hole that appeared black.
This idea seemed so crazy at the time that even Einstein himself didn't believe it. But over time, people started to wonder, what if the theory was right? What if these things really do exist? The observations here in Broome had set the stage. The hunt for black holes was on.
In the 100 years since, we've learnt so much more about black holes. We've even discovered that there's likely to be a staggering 100 million of them in our galaxy alone. That's why right now, some of Australia's smartest minds are working out how to find them. Wondering what they could mean for the laws of physics. Dr. Christian Wolff is one of these black hole hunters. His prey are some of the oldest and hardest to find black holes in the universe.
It is absolutely exciting to look for something that is rare, something that is not obvious to identify. They are hiding in plain sight among the stars.
When it comes to finding black holes, he's one of the world's best. And it's something he fell into by accident.
I suddenly found myself in the position that I was the guy who was finding all those black holes that other people had not been finding before. And I thought, apparently that's interesting, let's keep going.
Today, he and his students have made the journey to the Siding Spring Observatory, atop the Warrumbungle Ranges in New South Wales.
Have a look over there to the other side.
Yeah, I saw
What does it look like?
it. Looks like a storm.
A storm. All right.
I saw lightning in the clouds.
It's a rare opportunity for them to get 3 nights of continuous telescope time. But the weather is not playing ball.
Now this is useless, honestly. I mean, you've got a bit of clear sky over there, but this needs to move. This is an optical telescope, so it's got to see light from the stars. If there are clouds, we're not going to see stars, let alone black holes that are 13 billion light years away. So we really need a clear sky, otherwise that's a night lost. Don't ever bring an umbrella to an observatory, it's a bad omen.
Apart from the prospect of rain, the stakes are high. Finding black holes amongst the billion trillion stars in the universe is a tricky task.
That cloud is receding.
Yeah.
I wouldn't have
Getting
believed
more
it.
and more clear skies.
As the night closes in and the first stars thankfully begin to appear, Christian prepares the 10-metre high telescope.
We're here for 3 nights, so we get 3 chances for a good night. We have enough things to look at for more than 3 nights. We're hoping to get through as much as possible. Every night we lose is a night lost, and we'll come back in half a year's time. All right. Welcome to our telly. It's a 2.3 meter sized telescope. That means the mirror inside the telescope has over 2 meters of diameter. The whole structure is over 10 meters tall. But we can look for 13 billion light years with it.
He and his team will be looking for distant signs of supermassive black holes, the largest type of black hole we know about.
Tonight, we're going to look at 12 objects in the sky, of which 2 or 3, hopefully, are actually growing supermassive black holes. We've prepared for this night for many, many weeks, and now is the chance to nail what are we looking at? Are we going to find these things or not? Now is the time.
It's a long night ahead. But how do you look for something that's completely invisible? Luckily, you don't always need to see something to know that it exists. Wind is a classic example. We can't see it, but we can see its effects every day. And that's how scientists first pinpointed where black holes might be, by finding indirect evidence of their existence.
I think this is the coolest movie that I have ever seen. Astronomers have mapped the motion of stars at the centre of our galaxy over the last 25 years, and some of them have made a complete orbit.
At incredible speed. They're circling around something extremely massive, 4 million times the mass of our sun.
Yet when we look, there's nothing there. This is the first really strong evidence that what's at the centre of our galaxy is a black hole.
It's amazing that the gravity from something invisible can make stars orbit so rapidly around it. But it's when the black hole pulls those stars into it that the real action happens. And that's another way hunters are trying to find and study them. Astrophysicist Brad Tucker is a black hole detective. The clues he's looking for come from the moments when chunks of matter are sucked into black holes by their extreme gravitational field.
We can actually see them eating. We can see distant galaxies, millions and billions of light years away, consuming material. And when we say material, we mean gas and stars and stuff that you find in a galaxy. And we see it because it emits light. It emits energy that travels all across the universe and lands on our detectors on telescopes here on Earth.
Black holes have a reputation for being cosmic vacuum cleaners that devour everything in their path. But the truth is more subtle.
Bagel! So this is Bagel the Beagle. She's my 10-year-old puppy. She's a turkey lover. And she's kind of like a black hole. If I were to give this turkey to her right now, she would consume it entirely. Just like a black hole, if you were to put a large chunk of stars right next to it, it eventually would be consumed. But she won't feed all the time, much to her dislike. She loves to eat, but she can only eat as much as is around her. She occasionally sleeps. And also, just like a black hole, she has a physical limit to how much she can have in her stomach. But she sometimes even presses that limit, to my surprise.
So if a star, planet, or other matter gets too close to a black hole,
Hello, welcome.
then they're consumed by the immense gravity and destroyed. And if there's no space food around, the black hole will lie dormant and eventually even die. As so often happens in science, it was the rare opportunity to look at a black hole in a different way that gave greater insight and brought some incredible surprises.
Zero and liftoff of the Delta II rocket with Kepler.
The Kepler Space Telescope was launched in 2009. Its mission was to discover Earth-sized planets orbiting other stars. But its ability to stare into deep space brought with it other benefits. Kepler also gave scientists their most detailed view ever of black holes feeding. It did this by measuring subtle fluctuations in bursts of energy emitted from the spinning disk of gas around the black hole, known as the accretion disk.
So, when we're looking at this Kepler data, we're just measuring changes in light. You see all these fluctuations. This is literally the black hole feeding in real time. And then the brighter it gets, we just had a big event. And this happened pretty fast. That was an 85-day period that we just watched, that you can see with your eyes through the data of Kepler.
Because it was a space telescope, Kepler allowed astrophysicists to observe black holes 24 hours a day, 7 days a week. Unrestricted by weather or by daylight.
We can look at the universe in a way that is on our time scale, something that we can relate to, that in the scale of me going to bed and waking up, a black hole has gone to sleep and woken up to feed again.
And the data revealed much more than they could ever have imagined. For the first time, we've seen the frequency at which black holes devour intergalactic material.
Now, these smaller events, this one only lasted for about a day. Clearly, we would never see this from the ground. And there's all these little snacks that happen on less than the scale of a day.
It also reveals the scale.
In order to create this amount of energy, it must be consuming hundreds, if not maybe thousands of stars, or a big pocket of gas. So we're talking about on order of thousands of times the mass of our sun being consumed in 5 days.
And even the unpredictability.
We've even seen a star come in, get mostly ripped by the black hole, but then the rest of the star goes out. So we've actually seen a black hole chomp on a star.
This work has helped move our understanding of black holes beyond being simple gravitational vacuums to knowing them as more complex and varied phenomena.
It's allowing us to spy on the secret lives of black holes, the in-between phases, their snacking phases. It is what we call a game changer.
As our observations are able to better characterize black holes, we're also getting better at using that data to help us predict things about them. We can now calculate that a black hole is born every second in the universe. And so far, everything we've learned about black holes makes sense according to the mathematical theories proposed by Einstein. His ideas about gravity explain so much of what we've seen. But as we close in on their secret world, we're starting to uncover a few surprises.
we've discovered some very distant black holes that have grown so big so fast that we have no explanation for how they could possibly exist.
And as so often happens, it's the anomalies that have got scientists interested. Back at Siding Spring Observatory in New South Wales, the weather has cleared and the hunt for black holes is on. A year ago, Christian Wolf discovered the fastest growing black hole that we know of in the universe. Now he's hungry for more.
Yeah, looks good.
He wants to look back over 12 billion light years and find ancient supermassive black holes that appear to break the rulebook.
Our mission now is to find the most massive and fastest growing black holes. We want to figure out how black holes can grow and how they first formed at the beginning of the universe, in the early stages of the universe. And that means finding the fast-growing ones and the really massive ones, because they are the hardest ones to explain.
As gas falls towards one of these supermassive black holes, it gets super bright, and we call it a quasar.
A quasar is a black hole with all that heat radiating stuff around it. A range of storm clouds that are being swirled around. There's a lot of energy there. There's a lot of radiation coming out that we can study.
It's Christian's ability to recognize potential black holes amongst the vast number of objects in space that makes him so successful.
We can see all the objects that are there. We know the positions and the brightness and the colors. Then we pick out our candidates for these supermassive black holes, and then we point this telescope at them.
By splitting the white light emitted from the accretion disk into different wavelengths, Christian can detect the precise mix of chemical elements in the radiation.
Every chemical element, oxygen, iron, magnesium, leaves characteristic fingerprints. It absorbs the light at specific wavelengths. We'll be able to recognize these fingerprints or other features and then see, now we know we're looking at this type of a star. Or actually, wait a minute, we are looking at a fast-growing black hole with its accretion disk around and with storm clouds that are glowing in all sorts of elements and so on.
And to everyone's surprise, our camera's barely rolling when the very first object they look at seems to have that promising chemical fingerprint.
As you see, that's basically no signal, and that's all noise.
That's the sky.
Yeah, that's just the sky. However, if we actually do a proper extraction, we see that.
Right, was I allowed to see this?
The night has just started, and they've already found their first supermassive black hole.
Come on, that's a beauty. We're looking at a spectrum of a quasar, a supermassive black hole in the early universe surrounded by an accretion disk. The heat from the accretion disk gives us that sort of baseline light here, and that's magnesium glowing in those clouds. That's silicon glowing in those clouds. Here is nitrogen glowing, and that's hydrogen glowing. There's oxygen there as well. These elements all apparently formed very early in the universe. The first hit. This is what we came for. Which one is that from the list?
The first one that
The first one?
that you said was interesting.
1 out of 1, I'm just stunned. Sorry.
But Christian is doing more than just stalking the skies for a single supermassive black hole.
If that was all we got, we could go home happy now. But of course we want to get more.
Sure.
His mission is to collect the data from as many as possible.
We're trying to smash the records, so we don't know how many there are there. We have no expectation of how many we are likely to find, so each one counts and each one makes a difference.
The reason? To solve the complex problem of how they got so big.
I wonder how they have formed, and physics doesn't provide a way to do that within what we know. So I want to map out the demography of those black holes and their early growth, and then we can infer from that what exactly is the problem that we have to solve here. The problem is likely bigger than we have acknowledged so far.
The answer lies in two possibilities that could change what we think we know of the universe forever. Either they were formed in the Big Bang.
If we find that they've been growing slowly and they started out very massive, very close to the Big Bang, then we have a rather profound mystery here. If the Big Bang made black holes, Jesus, what else is possible then?
Or they are growing in a much faster way than we previously expected, defying our current understanding of the laws of physics.
These things are growing faster than what we think we see, and also faster than what we think physics allows.
And to solve that mystery, Christian and his students have to do what they do best.
Definitely.
Yeah, it is another one.
Look at these bumps. What is that?
They've found another supermassive black hole, and it's even bigger than the first.
Between 15 and 20 billion solar masses. So, you know, we're really adding them at the top end. They're extreme. They're wild places, but there's only few of them and they're very hard to find. And I just like the hunt. I just like to pinpoint them and say, gotcha! Gotcha! It was nearly impossible, but here you are. We've got proof.
There's never been a better time to be a black hole hunter. But how you look shapes what you see.
Until now, everything we've learned about space has come in the form of light. It might have been radio waves or X-rays or visible light, but it's all just light.
But there's a huge amount of stuff that takes place in the universe that we can't see because the light that it makes doesn't reach us.
In our hunt for black holes, we've recently made a groundbreaking discovery: that the universe was talking to us in a language other than light. It's as though we've only been using our eyes, and for the first time in our entire lives, we can now hear as well. What we've discovered are gravitational waves.
It's an idea that Professor David Blair has taken a lifetime to uncover.
We may be able to detect the occurrence of, for example, planets, large planets falling into black holes, or even two black holes colliding with each other.
If they were detected, they could once again test Einstein's mathematical explanation for the universe.
If we discover gravitational radiation, it will confirm Einstein's theory of gravitation, or possibly disprove it and show that a new theory has to be applied.
For the past 45 years, David has been inventing machines that could hunt for gravitational waves.
If I tap it, it'll ring, as you can hear. And
it took his dogged Aussie ingenuity to help accomplish the near impossible.
This is maybe one of the most difficult things that humanity has ever attempted. And many people for many decades have been been talking about these hypothetical waves. You're never going to succeed in detecting these waves. You know, aren't you wasting your time? We believed that, there was a holy grail, that we would get there in the end. And Of course, time has proved that's the case. We're feeding this black hole. Whoops. A few stars are colliding, and the mass is increasing.
Today, he's showing what gravitational waves are to the next generation of young scientists at the Mount Lawley High School in Western Australia.
Whoa, and that one is a very massive one. And do you notice that the space-time itself was oscillating up and down? Space-time is elastic. That's what Einstein said. And if space-time is elastic, then you can ripple it. You can send ripples through it. Those are gravitational waves.
David was an integral part of a team of physicists around the world that developed the technology that let us first hear two black holes colliding.
Black holes were 30 times as heavy as the sun, and yet they were going around each other about 100 times a second. Can you imagine that? 100 times a second. And then they collapsed together and gave out a vast burst of gravitational waves that travelled through the universe for more than 1 billion years before they got to the Earth. And it was the biggest explosion ever measured by humanity. And yet it was pure gravitational energy and we could hardly feel it.
Gravitational waves are an unstoppable phenomenon. They plough through planets, stars, dust, everything. And unlike light, no matter what, they make it to Earth. But key to finding and understanding these incredibly tiny, low-frequency vibrations was to build extremely sensitive listening devices. To find out more about how they work, I'm meeting David at the Gingin Gravity Research Centre in Western Australia to see one of the world's first gravitational wave detectors. I'm really excited to see this because this was something that I studied as a student, how these work, but you actually worked on it. So what do you think when you're looking at this?
Well, I guess I remember struggling with things like a leak in this pipe.
Yeah.
And, 2 o'clock in the morning deciding, let's rush to the workshop and get the welding kit and see if we can weld up a leak to make the thing work. And my entire life has been a quest for the perfect oscillator.
And is that what this is?
And this one is one of the best. You tap it like this.
Yeah.
It will ring for more than a month after you've started that vibration.
That's a pretty good bell.
If a gravitational wave passed through that bar, it would make the bar vibrate a bit. The trouble is, everything is always vibrating, so you had to work out how to get rid of that vibration.
We live in a world that vibrates. Weather, trains, and even walking can cause these highly sensitive detectors to move. It was David's obsession with filtering out these large vibrations that eventually led to the detector's success.
And then we could pick out tiny vibrations which are about 100 billion times smaller than the size of an atom.
That's ridiculous. The fact that you can measure anything that tiny just seems like it shouldn't be possible.
Everybody else doubted that this would work. It was almost too good to be true.
This is technology that no one had ever built before. No one knew how to build it. David's niobium bar detector was capable of detecting gravitational waves if they'd gone off in our own galaxy, but not of detecting black holes colliding further away in the universe. To do that, they would have to go bigger and better.
We learnt all the intricate details about making incredibly sensitive measurements, and we're able to apply that to laser interferometers.
LIGO is currently the world's largest and most sensitive gravitational wave detector. With 2 vacuum-sealed arms, 4 kilometres long, hypersensitive mirrors, and a laser beam bouncing between them, it's probably the world's largest ruler.
The gravitational wave stretches the space between two mirrors. A gravitational wave is a wave of stretching and shrinking space. Laser beam reflecting between the mirrors measures the difference in length, and that's how we detect the waves. That's how they were successfully detected.
On the 14th of September 2015, LIGO detected its first observation of a gravitational wave. As one of the pioneers, for David, it was a huge triumph.
I'll open the door and show you.
And there, as part of the team, was his son, Carl.
New, bigger, better instrument over there.
He's taken time out from his research to give us a quick tour. So in that first gravitational wave detection, you had a couple of black holes colliding 1 billion years ago, and the ripple in space-time has travelled all the way here until it was detected by this detector immediately behind you.
Detected right here. This detector was the most explosive event humans have ever heard. These two black holes colliding, making more energy than all the stars in the whole universe. Being detected is the most minuscule thing we've ever measured. The movement of one of these 40-kilogram mirrors by 1,000th the diameter of a proton. Just amazing.
Awesome. So this is really the heart of the LIGO instrument.
This is exactly the heart of the LIGO instrument. I would say that beam splitter is the real heart of the LIGO instrument. So at that beam splitter, if there's a gravitational wave, more light goes down this arm. If there's no gravitational wave, all the light's reflected back into the input arm here.
That's really exciting. Mm-hmm. It's like right there.
It could be detecting gravitational waves right now.
Exactly. The detection of a gravitational wave event brought with it the ability to experience the universe in an exciting new way. It turns out, gravitational waves are something we can hear. But to listen to them, they had to be extracted from the enormous amount of data that LIGO collects. Eric Thrain from Monash University was part of the team that deciphered the signal from the cacophony of noise that LIGO detects.
Gravitational wave astronomy is a quintessential big data problem. We measure the disturbances in space-time, but we have a huge amount of noise in these measurements. So the data analysis problem is to comb over this immense data set and disentangling all of these very quiet sounds. And our job as gravitational wave astronomers is to find that sound and understand it. So it's a little bit like being in a symphony hall and listening to a full orchestra. And most of this orchestra, though, is making sounds that you're not interested in. That's the noise. But there's one instrument, the binary black hole instrument, and that is making a sound that you want to hear this one sound and pick it out from the entire orchestra.
To find that single instrument in the symphony of space-time, Eric and his colleagues combined the formidable forces of a supercomputer and Albert Einstein.
Einstein's theory was very specific in telling us what a gravitational wave signal from two black holes sounds like. But the problem is that there are millions of different ways in which you can assemble two black holes. Exactly how heavy are they? How fast are they spinning? And so in order to take into account all the different possibilities, we tell our computers what gravitational waves sound like according to Einstein's theory of general relativity, and then they have to check all these possibilities. And these computers are essentially panning away through this data, sifting away the trash, trying to isolate these moments where something spectacular happens, where Einstein's theory produces these beautiful gravitational wave sounds.
A black hole chirp sounds like this. It's kind of a silly sound. It starts at a low pitch as the two black holes are far apart, but as they get closer and closer together, losing energy through gravitational waves, they move faster and faster, the sound gets higher pitched, and it sounds like a slide whistle until it finally clicks, and that
clicking sound at the end, that's two black holes in a final death spiral smashing into each other, releasing a huge amount of energy. It's a small noise and it's a goofy noise, but it represents the most catastrophic release of energy in the universe since the Big Bang.
It was an astonishing, audible glimpse into the mysterious world of black holes. Something only possible because of a clever combination of ingenious engineering and data science. But more than that, gravitational waves allowed scientists to experience space-time exactly as Einstein had predicted over a century ago.
Einstein has a very nasty habit of being right. This is one of these astonishing moments in science when many decades of research are required to confirm a prediction, and then it comes and the results are beautiful.
Every time we find a new way of looking at a black hole, it reveals more about the universe and the world around us. So just imagine what we might learn when we can take a peek at one for the first time. Trouble is that because of their nature, you can't see a black hole. But it might just be possible to see the very edge of one. It's a volatile place called the event horizon.
Imagine that you're swimming at the top of a waterfall, which is a really bad idea, by the way. If you're up there and far enough away from the edge, the water's moving slowly and you can comfortably swim against it. But as you get closer to the edge, the water speeds up and it gets more and more difficult to swim away. The edge of the waterfall is like the event horizon of a black hole, except now the thing that's flowing isn't water, it's space itself. And nothing, not even light, can swim fast enough against the waterfall of space to escape from a black hole.
It's a gravitational force so extreme that it pushes the limits of physics. And yet, we can use Einstein's theory to predict what it might look like. But
what if, when we see a black hole for the first time, we discover something different? What if we discover Einstein didn't have all the answers?
I've come to an observatory above the clouds, high atop the peak of Mauna Kea in Hawaii, where they're trying to take a closer look. It's a project with an ambitious goal. It's an unprecedented feat in astronomy, to take a photo of the supermassive black hole Sagittarius A star at the centre of our galaxy.
So we're headed up to...
The project is called the Event Horizon Telescope.
Welcome to the James Clerk Maxwell Telescope. It's one of the most important telescopes in our network.
Dr. Jeff Bauer and his team hope to capture an image of something 24 million kilometres across, but 26,000 light years away.
Why is it called the Event Horizon Telescope?
So the event horizon is the region around a black hole where no information can escape. And we've designed our telescope to get in as close as possible to the event horizon.
It's crazy to think that you might be able to actually see that close to a black hole.
What we want to do is get the best proof possible for the existence of black holes.
It's an almost impossible data-led task, connecting 9 radio telescopes across the globe, all in different time zones, and each with a different view of the sky.
So it's like getting a little piece of the picture from all of these different ones, but you can't put it together until you bring them all into one place.
We're building one big mirror out of those pieces. We're seeing the finest resolution that you can possibly see from a telescope, better than the Hubble Space Telescope, better than any other telescope on the ground.
It's effectively a curved mirror 9,000 kilometers in diameter, which makes it the world's biggest camera.
Welcome!
Thank you.
To my baby.
Very excited to be here.
And it just so happens, one of the scientists charged with taking the picture is my old office mate, Australian, Dr. Jessica Dempsey.
You look above us, every single part of this dome, even all of these cables here,
yeah,
these all rotate with the telescope.
Yeah.
The accuracy on sky for us needs to be finer than a human hair. Our pointing was off one time. Couldn't figure out where it was coming from. The guys came up and looked on this track and they found a squashed cockroach. Just a tiny cockroach on the track was enough to put a 300-ton telescope a little bit off.
Jessica's formidable task is to manage the incredible detail behind the Event Horizon project.
Well, we actually have to know the timing of the collection of these signals to a billionth of a second at every single one of these telescopes in order later to make sure we were all looking at the same thing and we were all looking at the same thing at the same time. We've made a dish the size of the planet. To give you an idea of how small a thing you can now see, if you were sitting in a pub in Perth, you would be able to see a guy sitting in the pub in Sydney. Not only would you be able to see him, you'd be able to see his eye colour and you'd be able to see the brand of beer he was drinking.
That's a pretty good telescope.
I think so. And that's exactly what we need to be able to see and resolve the black hole at the centre of our galaxy. In fact, it's just enough.
4,092 metres is not high enough to escape today's wind and rain. It's just one of the many problems Jess and her team around the world must navigate in order to get the perfect shot.
So this is your control centre, essentially.
That's right.
You can see what's going on at every telescope.
That's right, but I only have control over a tiny, tiny fraction of the things that can actually go wrong. So I get stressed every time I look at this. So if we wanted to observe right this minute some of the things which need to happen, well, one, the weather needs to be good. So we'd be right out.
Needs to be good everywhere.
And it needs to be good all over the planet. You can imagine how hard that is. The second thing I'm looking at here is I'm like, okay, can we actually see the black hole? Is it up in our part of the sky?
Can we see it right now?
And I was actually and this is actually a really good time to take an observation. I kind of just want the weather to clear up and we can get going, because right now is one of these rare times when most of the telescopes around the world are able to see the source.
It's an audacious feat of global teamwork in some of the most extreme places on Earth, like Antarctica and the Atacama Desert in Chile. Timing is crucial. Often they have as little as 1 hour to observe and record petabytes of data to make the picture.
We are stacking impossible task on top of impossible task, and this shouldn't work. You are just really desperately hoping that you're not the one that has a problem. You name it, we've messed it up. There was a night when we were like, we don't know what it is, and we're like, oh, we should open the roof.
To give you an idea of its immense power, the Event Horizon Telescope has already revealed astonishing detail of the cloud of superhot gases at the centre of the Milky Way.
And the most exciting thing that we found here was in this bright yellow here, and we called it a twisted ring. And it's a twisted ring of exceptionally heated up gas that is actually rotating around what we believe is the black hole at the centre of our galaxy, which is positioned around about here.
It's all part of piecing together that other highly sought-after picture. Sifting through the combined data from each telescope and its view of the sky to extract an image that one day soon will let us all set eyes on a black hole for the very first time.
With gravitational waves, we heard it. And then we snuck a bit closer and we could see the evidence of the stars nearby, reacting to its presence. Now we've snuck up a bit closer, and we're going to actually see the silhouette of the black hole. So finally, we're going to catch a glimpse of this guy, and I'm pretty excited. And he's in here somewhere.
And what exactly will that image look like? Well, for now, it's up to one of those hunting for it to do his best to describe it.
We're going in and we're going to see the shadow that the black hole casts. And that shadow is the bending of light that originates near the black hole and makes a beautiful ring around the black hole.
So you're going to see the silhouette of the black hole against the glowing of the background light that's being bent around it.
That's exactly right.
Capturing the photo of Sagittarius A star is a truly remarkable project, which is part of an even bigger picture. What it reveals could change the way we approach both physics and the science of the universe itself.
So first off, if the ring just isn't there, that would be shocking. All of Einstein's theory tells us that the ring should be perfectly circular. And so if we see it squashed down, or if it's imperfect in some sense, or if it's not even a ring, if something truly bizarre shows up, then that tells us that something about general relativity breaks down when you get into this extreme regime.
It'd be pretty surprising to us both, I think, if Einstein's theory proved to not be right. What would you feel if that has happened?
It's always more exciting to show the theory is wrong. And, you know, it would be an amazing thing to discover that the theory of general relativity is incorrect. It's not very likely, but it would be the greatest moment of my scientific life to be able to show that.
It's a photograph that I can't wait to see. And even though it might look different to how we imagine, I think it's going to be another one of those images in the story of science that unlocks a whole new era of understanding.